Generally in physics, we deal with two types of quantities. We deal with vectors and scalar quantities. A scalar quantity is any quantity in physics that has magnitude but no direction associated with it. Some examples are speed, distance, age, and heat. An easy way to remember speed as an example is that they both begin with the letter S. An example of speed would be 20 meters per second. Okay, so magnitude, which means number, would be the value 20. The units are meters per second. Because there's no direction associated with it, we have deemed it as a scalar quantity. So the direction does not affect the measurement. Magnitude is just a numerical value, right? So magnitude means the number, the value, etc. Okay, so speed, distance, age, and heat all do not depend upon direction. There are other examples of scalars that we will talk about this year. Can anyone think of one? And another example of a scalar, a type of quantity that does not depend on direction. Usually students come up with time, right? Time is also a scalar quantity. We cannot move forward or backwards in time. Time does not have a direction. So time would also be an example of a scalar quantity. As would temperature. The second type of quantity that we deal with in physics is called a vector quantity. A vector quantity has both a magnitude and a direction. So the direction plays a component in the identification of this value. Examples of vectors are velocity, acceleration, and force. An easy way to remember velocity as a vector is they both begin with v. Speed and velocity differ, as velocity depends on direction and speed does not. An example of velocity would be 20 meters per second north. 20 again would be the magnitude, meters per second would be the units, and north would be the direction. Acceleration and force are also examples of vectors. An example of acceleration would be 10 meters per second east. Example of force would be 5 newtons west. We represent vectors pictorially. We can represent a vector using an arrow. The length of the arrow corresponds to the magnitude of that vector, and the orientation of the arrow conveys the direction of that vector. Can be due north, can be northeast at an angle, depends on the orientation of the representation. In physics, we use vectors to determine and understand how and why objects move. Scalar quantities can simply be added together or subtracted from one another without needing to reference direction. Vector quantities, however, have their own rules for calculation. We'll first start out talking about vector addition. Vector addition is simple if the vectors are pointing in the same direction. If vectors point in the same direction, we add the vectors from tail to tip. Let's take a look at an example of what that means. Example 1, a man walks 54.5 meters east, then another 30 meters east. Calculate his displacement relative to where he started. So 54.5 meters east Because we know the direction there, we can see that that is a vector quantity and not a scalar quantity. The second leg also denotes a direction, 30 meters east. That is also a vector quantity. We can represent these vectors pictorially using arrows. So let's start out with our first vector. So a man begins at the origin. He then walks 54.5 meters to the east. Note how our arrow is pointing due east. We'll label that vector with the magnitude as well as the direction. So from the origin, he walks 54.5 meters in the east direction. Then another 30 meters in the east direction. So we're going to add the tail of our next vector to the tip of our first vector. We call that tail to tip addition. Note how the second vector is shorter in length to represent a smaller magnitude, but the arrowhead points in the same direction, east. We again label our vector. To find his total displacement from the initial location to the final location, we add the vectors when they point in the same direction. Therefore, the total displacement is equivalent to 84.5 meters in the east direction, as the man ends east of where he began. Let's take a look at an example of vector addition in which both vectors are not pointing in the same direction. Before we move on, please note that the size of the arrows convey magnitude, and the way that it is drawn conveys the direction. Okay, so vector addition rule number 2. If vectors point in opposite directions, subtract them. So in this example, a man walks 65.5 meters east, then 20 meters west. Calculate his displacement relative to where he started. So again, we're going to use a pictorial representation to denote the vector. So we're going to start at the origin and draw a vector. Label that vector 65.5 meters east. We are then going to add the vectors from tail to tip. So the tip of the second vector should line up, the tail of the second vector should line up with the tip of the first. However, in this example, the second leg of motion needs to point the opposite direction as the vector points in the opposite direction compared to the first. So we will represent tail to tip. Note how the arrow points in the west direction and how the size of the arrow is significantly smaller than the original vector. To denote the size difference, we again label that vector as 20 meters west. To calculate the displacement relative to where he started, this is the origin of the man. This is the final position of the man. So in order to find the displacement, we must subtract the length of the second vector from the length of the first. So I'm going to subtract 20 meters from 65.3 meters. We get a length that is equivalent to the vector denoted on the screen. The magnitude of the vector is 45.5 meters, and that vector points in the east direction, as the man ends east of where he began. So he ends east of the origin, so the direction of the displacement would be east. The magnitude of the displacement is 45.5 meters. Okay, so let's take a second and pause. Take a look at this checkpoint question. Rank the magnitude of the vectors from largest to smallest. Please pause the video while you rank. Unpause the video when you are ready to review your ranking. The vector ranking is as follows. Vector E is larger than vector A. Vector A is larger than vector D. Vector D is larger than vector C. And vector C is larger than vector B. Remember that the lengths of the vectors represent the magnitude or the relative size. Now that we know how to add and subtract vectors that are in the same and opposite directions, let's take a look at a scenario in which we have two vectors that are not in opposite directions or the same direction. So still an example of vector addition. Example 3. A man walks 95 kilometers east, then 55 kilometers north. Calculate his displacement relative to where he started. So let's stick with our previous method. We'll take 95 kilometers east, and we're going to represent that as a vector. If we add, so here's our origin. Our man walks 95 kilometers to the east. He's now located here. If from that location he walks 55 kilometers north, how would we draw the second vector relative to the first? Considering the tail to tip rule, we would draw the tail of the second vector right in front of the tip of the first. So we're going to draw our vector in the north direction, tail to tip with our first vector, and label it. Okay, so now what? Do we add? Do we subtract? Well, technically here, we should note that vector 1 and vector 2 are perpendicular to one another. They create a 90-degree angle. What do we know that's special about a 90-degree angle? It's present in a right triangle. In right triangles, we know a lot about trigonometry and trig identities to help us solve for additional information. We could quite easily add a third side here and create a right triangle. This is still an example of vector addition. So in vector addition, if vectors are perpendicular to one another, we still add them tail to tip, but we use trigonometry to calculate the resultant, or the distance from where we start to where we end, just like we did in the previous examples. This time, I'm going to represent it on a XY coordinate plane, just to make it easier to visualize. So here's the origin. Our man walks 95 kilometers to the east. Then he walks straight north for 55 kilometers. We need the distance, or displacement rather, in this case. We need the displacement from the initial location to the final location, which we call the resultant displacement. To find that length, we draw a straight line from the origin to the tip of our last vector. So from the origin to the tip of our last vector, we call this leg the resultant. It also represents the displacement. So now that we have a right triangle, we can use trig and Pythagorean theorem to identify the magnitude of this resultant vector. We label this resultant vector as a capital R. The arrow above the R represents a notation that suggests it's a vector. We also label the y component of that vector as R sub y, and the x component of that vector as R sub x. Can you catch something that I just wrote on the screen that is incorrect? This is the y component of the vector as it is present in the y. This is the x component of the vector as it is present in the x. So the x and the y subscripts need to be switched. The x component of the vector is along the x-axis, while the y component of the vector is parallel to the y-axis. So this is the x component of the resultant vector. This is the y component of the resultant vector. But we very clearly see a right triangle. So we have two sides of that triangle, and we're missing a third side. So if you have two sides of a right triangle and you're missing one side, what can you use from trig to identify the length or the magnitude of that last side? Hopefully you're thinking Pythagorean theorem. We know that the equation for Pythagorean theorem is a squared plus b squared equals c squared, where a is the adjacent side, b is the opposite side, and c is the hypotenuse. So technically, a is the x component of the vector squared. B is the y component of the vector squared, and that is equal to the resultant vector, also the hypothesis, which we use a capital R to represent, squared. If we're looking for R, we want an equation in which R is by itself. To do that, we take the square root of both sides of the equation to get the equation R is equal to the square root of the x component squared plus the y component squared. And this will be our standard equation that we use to find the resultant vector. So again, we're going to use this equation to find the resultant vector. So this is an equation that would go on your note card. Now that we have an equation derived from Pythagorean theorem, we can use that equation to find the displacement or length of this vector simply by plugging in. So I'm going to take 55 kilometers and square it. plus 95 kilometers squared, square root of that whole quantity. When you type that into your calculator, you will find that R is equal to 109.8. What are our units? Kilometers. Note that R is the hypotenuse, so it should be longer than both sides. Double checking, that's true. So this is our resultant displacement. The magnitude, right? This is the magnitude of the displacement. Okay, what about the angle? Or rather, what's the direction? Is the direction east, north, north of east, east of north? If you were to give your friend directions, so they're lost in the woods, right? Or you're lost in the woods rather. So you're stuck here and you're trying to give your friends directions to get directly from the beginning of the path to you as quickly as possible, right? You would need to tell them exactly what angle from the origin and what direction to travel in order to get to you. So if you think of this coordinate plane like a compass, right? North, due north, would be at the top of the y-axis, while south would be at the bottom of the y-axis. East would be to the right of the x-axis, and west would be to the left of the x-axis. So the angle is between our resultant and the east axis. We need to figure out that angle. If we have 3 side lengths and we're looking for an angle, what can we do to find that missing angle? Hopefully we're thinking trig identities. So we can really use any trig identity. The easiest and most consistent trig identity to use when solving for resultant vectors is tangent. So first we're going to derive the standard equation. So in this case, theta, the angle, is located between the resultant vector and the x-axis. So if theta is between the vector and the x-axis, the tangent of theta would be the adjacent side over the opposite side. So it'd be the x component over the y component. So tangent is the opposite over the adjacent side. The opposite side, the side opposite to theta, is the y component of the vector. The adjacent side would be the x component. So the standard equation would be that the tangent of theta is the y over the x component. So r sub y divided by r sub x. In this case, however, right, we don't have theta. So to find theta, or solve for theta, we'd have to take the inverse tangent of both sides. So theta would be equal to, as long as the angle is between the vector and the x-axis, theta will be equal to the inverse tangent of the y over the x component. So that's our standard equation. Now that we have our standard equation, which should go on your note card, we can calculate the angle. So let's go ahead and do that. So theta will be equal to the inverse tangent of the y component, which was 55 kilometers, over the x component, which was 95 kilometers. So we're going to type into our calculator inverse tan of 55 over 95, and we get 30.06 degrees. Please make sure that your calculator is in degree mode for these types of problems. Your calculator must be in degree mode because the angles that we are utilizing here are in degrees. Okay, great. So we have the magnitude, we have the angle. Last step is to label the direction. So if you think about this here, we start at the origin, right? From due east, the person would need to go north. So the axis in which the resultant vector is measured upon is the cardinal direction that goes second. So theta is in between the resultant and east. So the person is walking north of east. Another way to think about it is from due east, the man walks north. So it's north of due east. So again, the vector here is measured, or the angle here is measured between the vector and east. So east comes second in our label. So our complete direction would be 30 degrees north of east. Our entire resultant, we take the three parts that we determined and we write them all out. So our resultant vector is equal to 109.8 kilometers. That's the magnitude of our vector, the units. The direction is 30.06 degrees north of east. And that's our final answer. So that was several steps. When we have vectors that are perpendicular to one another, we must first use Pythagorean theorem to find the magnitude of the vector. Then we use trig to find the angle between the vector and the axis. We then used cardinal directions to further label the angle. The cardinal direction in which the angle is measured against comes second in the statement, comes after the word of. So let's take a look at a comprehensive procedure. So again, we found the resultant vector, which is equivalent to the terminology finding the magnitude and direction of a vector. So if you're asked to find the resultant or the magnitude and the direction of a displacement vector, a velocity vector, an acceleration vector. This is the process in which you will use. The first step is to sketch an XY Cartesian plane. Starting at the origin, add the vectors from tail to tip. Whether there's 1 or 4, each vector is added from tail to tip, representing the magnitude by the length of the vector and the direction by the orientation in which it's drawn. The third step is to draw a line to connect the tip of the first vector with the tail of the last vector, and we call that the resultant. It makes up the hypotenuse of the right triangle that was created. After the resultant vector or the hypotenuse is labeled, you then determine and label the x and the y components of the resultant vector, which again we use a capital R to represent. So the x components should be written as R sub x, the y components should be written as capital R subscript y. The second to last step is to use the Pythagorean theorem to find the magnitude of the resultant vector. Using our shortcut equation, after the magnitude is determined, we use trig to find the angle and the direction. And that is how we find a resultant vector, or how we perform vector addition when two vectors are perpendicular to one another. Let's try another example. So example 4. A boat moves with a velocity of 15 meters per second north in a river which flows with a velocity of 8 meters per second west. Calculate the boat's resultant velocity with respect to due north. So we see a change here. We see that the values are now meters per second. Velocity is also a vector. We can prove it's a vector because we can denote in our example the magnitude, the units, and a direction. So we treat this as we've treated each other vector problem. We draw our xy Cartesian plane. We start at the origin and we represent our vectors using arrows. In this case, the first vector listed points due north. So from the origin, we draw a vector pointing due north and label it as 15 meters per second north. We add the second vector, the tail of the second vector, to the tip of the first vector, in which the magnitude is 8 meters per second and the direction is west. So how should the length of the second vector compare to the vector that's already drawn? We notice that the magnitude is smaller, so the vector should have a shorter length. Now that we've drawn our vectors tail to tip, we'll start at the origin and draw a resultant vector from the origin to the last leg, or the tip of the last vector. Now it's time to label our resultant vector, R, the x component of our vector, as it's parallel to the x-axis, and the y component of our vector as it's located on the y-axis. Our next steps are to use the Pythagorean theorem to find the magnitude of the vector. So give the video a pause and determine the magnitude of the resultant vector. Unpause the video when you are ready to check your answer from the Pythagorean theorem calculation. As we square 8 meters per second added to the square of 15 meters per second, square root of the entire quantity, the resultant vector has a length of 17 meters per second. What's our next step? Now that we have the magnitude, what else do we need? Well, a vector is considered final when we have a magnitude, units, and a direction, so we still need to determine the direction. Let's do this part together. So technically here's our theta. Theta this time is measured between the resultant vector and the y-axis. So this time theta is located with the y-axis. Okay, so if theta is between the resultant vector and the y-axis, the tangent of theta would be the x component, the opposite leg, over the y component. So our expression is different. Our expression changes depending on which axes theta is measured against. Again, we don't have theta, so in order to find it, we'll have to take the inverse tangent. So theta will be equal to the inverse tangent of the expression r sub x divided by r sub y. So that is our standard equation to find the angle when theta is measured according to the y-axis. So take a second, pause the video, and calculate theta. So you plug our x and y components into the tangent equation. We have inverse tangent of 8 over 15, which you should get 28.1 degrees is the angle. From due north, the individual would have to walk west. The angle is measured between the vector and north. So north comes after the of. Okay, so the cardinal direction in which the angle is measured against comes after the of when clarifying the direction. So from due north, we go west. So the direction is 28.1 degrees west of north. Our final answer is 17 meters per second, 28.1 degrees west of north. So I want you to take a second and think about, what does this mean? What does this mean? Can you describe in words the relation of this value here, this expression you wrote, and the boat previously noted in the problem? Okay, so technically, the water is moving north, 15 meters per second. In the water, a boat is attempting to drive west at 8 meters per second. Because the water has its own current, the actual velocity and direction of the boat is 17 meters per second, 28 degrees west of north. So this is the intended direction and velocity of the boat. This is the velocity of the river. Because the velocity of the river affects the velocity of the boat will actually travel west of north at an angle of 28.1 degrees at 17 meters per second. So that resultant represents the true magnitude of the boat when it's in the water.